Hello. Can you hear me? Hello. Oh, there you are. I love it. All right. Hello, hello. We'll get good morning. All right. So let's do this. So I'm going out of order. Oh, double. All right. Hello. Good morning, Al. Oh, wait, more people coming. Oh, I love it. Okay. Good morning, Alice. Good morning, Sydney. Good morning, DJ. Good morning, Loani. Good morning, Eric. Good morning, Maya. Good morning, Emily. Good morning, Lena. Wait, and oh, hold on. Okay, the chat. Um, why? Good morning, Maya. Oh, there's Tree. Okay, awesome front row seat. Okay. Good morning, Lena, for the good morning, Alice for the double. Good morning, Sydney for the double. Good morning, Loani for the double. Good morning, DJ for the double. Good morning, Emily. Good morning, Erica. Good morning, Tree for the double. Good morning, Ashley for okay. I don't know why that just happened. Oh, no, I don't want to block anybody. Okay. We'll switch this in a minute. All right, let's get rolling. Thank you all for handing in homework 3. Some of you have still, I fell a little bit behind, so many of you have gotten it back. Some of you have not gotten it back. Um, I'll leave it at that for the moment. Just a couple of quick things to remember. And of course, you can still, revise and upload for more points, all of that. Um, More people coming. Sorry. Good morning, good morning. I don't want to block anybody. Uh, Quick comments. Please always just do everything PDF, especially the exam that's coming up. Like, make it a PDF. If you don't know how to do that, I can show you. Like, it's always more doable than it seems to make something a PDF. Just please do that. Um, there's reasons. Also, always your final answers, please like circle the entire answer. Like the entire answer is something like at 200 seconds, the temperature, or or it would take 0.571 seconds to reach the original temperature again, or whatever. Like the final answer is a complete statement of the result and the condition, so to speak. It refers back to the original question. So a final answer is not just 0.571 seconds, or even really t equals 0.571 seconds. Like that's better. T equals 0.571 seconds is better than just writing 0.571 seconds, for example. But the ideal thing to write for all of the points is the amount of time it will take for the temperature to return to its initial value or whatever is t equals 0.571 seconds, or however words you want to use for that. That you're just pro tip, whatever. That's one play. You do need diagrams. Rule of, and also what I'm saying right now, I'm basing also partly on some conversations I had with people like after the end of class last time. Um, like we're still getting used to all of this. And again, the exam is just a big higher stakes version of everything we're practicing on every homework, like same routine, same expectations, same type of rubric. So whether we like it or not, we're getting used to it. It may all seem new to some of us, but it honestly is not meant to be mysterious or opaque, the expectations. I'm just saying, like, it may take some getting used to, but that's what it is. It takes some getting used to. Like so for example, and I'll move on in a minute, like I do always want a diagram at the beginning, especially if a diagram wasn't provided to you. You always want to present a diagram, and it may seem very, and I mean this serious, it may seem very sort of like um unobvious what would be included in the diagram or what kind of diagram, or how do you know when you're done with the diagram? But let me just repeat, the rule is the purpose of the diagram is to define every single constant and variable that you're going to be using in the math of steps 3 and step 4 or whatever. Every letter that comes up needs to be defined initially. How is it defined? As a label in the diagram. So whatever diagram can accomplish that is what you want to do. There may be choice, like, so again, for homework 3, just saying quickly, whether what I think is the most straightforward diagram to present right at the beginning would be a cosine graph that has T and D naught and omega, or 121, whatever, and you square, all in that cosine graph. But if you could come up with some other way or some combination of pictures to make every single one of those labels do their job, great. The point is to define all of the terms that you're going to use in the math. So that's oh, and here's an important thing. All of what I just said, hopefully, I don't whether you write it down or not, is true in general for any homework and for the exam. Okay, one thing in specific about homework 3, and again, some of you have not gotten it back yet. I apologize. But take a note of, and again, all of you could still do more of it if you want to get more points. Specifically in homework 3, and this is very specific to the exam, what I'm about to say. If you did not get all the points for step 3, general definitions and principles, one very possible reason, very common reason, is if you want to say that omega is the square root of 121, like, okay, I totally agree with that. And I think that's a major insight in the homework, that omega equals 11 radians per second, the square root of 121. That is totally true. And that is like totally huge, but it's so huge to the whole homework. It's such a major point, and it's so not obvious. Like, if you're starting to get used to that, that's great. If you're starting to get used to the idea that omega is the square root of the proportionality constant in the differential equation, if you are starting to see that and get used to it, good, because that's what homework 3 is like sort of meant to be reinforcing. Absolutely. But why is that true? If you're at the beginning of a document, whether it is homework 3 or an exam, that needs to be established. Why is the angular frequency of this cosinusoidal oscillation the square root of this constant in this differential equation? Like, that's a huge, like, it took us a month to get there. So why is it true? The simple, quick answer is because if you take 2 derivatives of that cosine expression, you get back to that differential equation. What I'm saying, and I'll move on, and I'm saying this as, again, if you want more points or if you want to know a major pro tip going into the exam, at least the first time in the document that you want to show that, and I guess if you want to show the cosine solution and show that the omega in that cosine expression is the square root of whatever is in the differential equation as the constant, you show that by taking 2 derivatives with respect to time of your cosine expression. If you did not get all the points in step 3 of homework 3, that may be why. And all you have to do is correct that and you'll get the points. Okay. And present a new document. That is again, and last thing I'll say, I'm going to move on. Like, self-sufficient document means you want to give the reader a piece of paper, a bunch of pieces of paper. You want to give the reader a document that provides everything the reader needs in order to navigate the document, which generally means providing all those tools up at the beginning of the document. Like, so you have to walk the reader through these understandings. That may even mean, like, put a title on the document. Like, that would be good. Like, pretend that the person who's reading your homework, it could be me, or pretend it's a TA or something like that. I don't know what it is until I open it up. Like you're going to tell me what it is and what's going on step by step through the whole thing. Again, I'm saying all this because I know we have an exam coming up. So it's all this is all just practice for what we're looking for there. Okay, but that's enough of that. Oh, and good morning. If I didn't say to Tree, I think I did good morning, Ashley. Oh, I guess I did. Okay. So that's that. You can still do stuff, blah, blah. And if you didn't get back homework through yet, I apologize. You will. But if you did, that's why. Okay, so I'm going to what am I doing? Oh, sorry. And I didn't even realize I wasn't on video. That's not on purpose. Sorry. That's bad, actually. I am here, I promise. And I'm not wearing pajamas or something. Hold on. Okay, yeah, that's okay. So picking up where, and I'm going to switch the view. Well, all right. I want to get back to where we were 2 days ago. Where we were was inspired by a question in the homework, question 1F from homework 2. That's what started discussion, but I need to teach a bunch of stuff that's motivated by that question. So the summary of where we got to at the end of question F. Well, at 1F and G, really, both. From 1F and G, what we established is that if we have that differential equation that describes simple harmonic oscillation, we have been saying up until now that a solution to that differential equation is, in effect, z equals z naught cosine omega t. We've been saying cosine omega t as the expression that satisfies the differential equation that describes harmonic oscillation. That's what we've been saying. What we just discovered 2 days ago, I'm going to switch the view now. What we just discovered 2 days ago is that, in fact, we could stick a constant into the parentheses from that cosine expression, and it still will satisfy the differential equation. Like the math does not get badly affected by sticking in a non-zero number into the argument for that cosine. Apparently, the math still works. I didn't know that starting all of this, but apparently after exercises F and G from the homework, I know it now. Now, so from here on in, so what we're really saying is, in retrospect, whenever we've been saying z equals z naught cosine omega t, we've really been saying z equals z naught cosine omega t plus 0. Like we've been assuming that the number in that parentheses has been a 0. Now we're saying it doesn't have to be 0 and the math will still work. So from here on in, what I'm going to say, we're allowed to stick a number in there and we're going to call that number phi, like this is a lowercase Greek letter phi or phi. And we're gonna say it could be any number. In fact, honestly, it could be like it could be subtracted or added to the omega t. And since it's being subtracted or added to the omega t, to cut to the chase, that phi, that extra number that we're sticking in, could be any number, right? As long as the number stays the same, could be any number, but it must be measured in radians. Why? Very quickly. Number one, if you're adding it to omega t or subtracting it from omega t is in radians. Like omega is radians per second and t is in seconds. So radians per second times seconds equals radians. So you can only add radians to radians. Like you can only add apples to apples or kilograms to kilograms. You can't add kilograms to meters, right? So if what was already in the parentheses were radians, then we got to add something to that. But furthermore, the point is the whole total in the parentheses has to be radians because we're going to take a cosine of it. I mean, and technically it could have been degrees, but we just don't deal with degrees anymore in this way in physics and math. Okay, so it's radians. It's an angle. So phi could be any amount of radians, could be stuck into that parenthesis, and the math will still work. We're going to call that constant from now on a phase constant. Now, here's the point. We discovered that it works mathematically, but this is a physics class. Like, that must mean something. Like the math that we're dealing with here is the description of a simple harmonic oscillator, some kind of system that acts like a mass on a spring. And side note, that's why whenever I say Z, I'm not trying to confuse you. When I say Z, that's my way of saying could be any variable. Like in our first homework, it was X, but then in your lab, it was theta. Then in the homework number 3, it was D. It could be anything standing for a measurement that depends on time, that varies in time. But if that measurement, if the second time derivative of that measurement is directly proportional to that measurement, with a negative sign, then that measurement is oscillating harmonically. Like that's what we're saying, right? So we're calling that Z right now to mean any measurement at all. And I'm saying that from now on, there could be this constant called the phase constant stuck into the parentheses. And if that's true mathematically, it must mean something physically. So what does it mean? What does it mean to add an extra bunch of radians or subtract a bunch of radians, from the omega t? Here's what it means. Well, in English, well, actually, it means the phase constant means a head start or delay, like, depending on whether it's like added or subtracted. It means the phase constant phi means a head start or delay in the cycle. Phase, the word phase, Phase, means portion of cycle. Like where are you in the cycle is what your phase is. What phase of the cycle are you in? So phi indicates like a head start or a delay with regard to the cycle. I'm going to do a quick example here. So A and B are two examples of what phi could be and like what that would mean. So example A, in the yellow on the board, if phi were equal to 0, like what does that mean? Like, and let me say, phi being equal to 0 is what we've been sort of assuming for the last couple of weeks. Like we didn't know there was a phi. We've just been treating it as 0 and we've been getting away with that. Like why? Like what does that mean? Well, what I'm saying is phi, if you like work out the math, which we're about to do, phi is an indication of the value of Z. It tells you where the whole system is regarding cycle. It tells you where in the cycle the whole system is at t equals 0. Like that's what it literally means. It's like where in the cycle are we at when the stopwatch starts. So I'll show you what I mean. Say phi is equal to 0. Again, I'm looking at example A here on the board. Say phi is equal to 0. Okay, then we would plug in 0 for phi, as I did with the yellow right here, right? And we ask ourselves, okay, if phi, the question is, what is going on with the variable with Z at t equals 0? Always, I'm saying phi is like an initial place in the cycle. So it's always indicating what's going on when t equals 0. So I plugged in 0 for phi because I'm doing that example where phi is 0. And I'm plugging it with red, I'm plugging in 0 for t because that's what I would always do. Oh, so, okay, got you, direct chat person, got you. Thank you for telling me. Okay, gotcha. So I want to make clear to everybody, like two things I just plugged in for 0. I mean, I just set equal to 0, two different values. The yellow one I made 0 because I'm testing what that would mean if phi were 0. Like if you scan below on the board later on, I plug in something else for phi. But I'm in red, I'm plugging in 0 for t because that's what I would always do if I'm testing what I mean by phi. So I plugged in both for 0 and I find that if phi is 0, then when t is 0, Z equals the cosine of 0. Now, the cosine of 0 is always 1. Always, right? You want to know that. The cosine of 0 is always 1. So, I'm saying what it means to say that phi is 0 is to say that when t equals 0, z equals z naught. What? That didn't sound like English. Let me tell you in English what I just said. I mean, it was true what I just said, obviously. What I'm saying is to not have a phase constant, to treat phi as 0, as we've been tacitly doing for the last couple of weeks, is to say that the whole experiment began at the top of the cycle, at the beginning of the cycle. When the whole experiment began, when we started our stopwatch, the initial value of the variable was the amplitude value. Like, to be concrete about this, in homework one, there was no phi at all because at t equals 0, the mass was at position 15 centimeters already, and it was held at rest at 15 centimeters. So that was as far as it was ever going to get. A cycle meant start at 15 centimeters, go all the way into the equilibrium, go past the equilibrium to negative 15 centimeters, and come all the way back to 15 centimeters positive, right? A full cycle meant all the way there to negative and all the way back to positive. If that's what a cycle is, in homework one and in lab one, you started your stopwatch when the object was at its maximum stretch from equilibrium. So that, which is a very convenient and wise thing to do. It's not the only possible thing to do, but it's a wise and convenient thing to do. So wise and convenient, we didn't really give it much thought when we did it. And that's what it means to say phi is 0. There's no delay or head start in terms of the cycle. You're starting your stopwatch at the beginning of the cycle. What do I mean by beginning? I mean amplitude position. Now contrast that, and I'm going to pause when I do this other thing and I'm going to ask you if you understand what I'm talking about here. But contrast that with, let's say phi is pi over 2, which is like a number. Right. And in fact, it's a pretty standard number of radians, pi over 2 radians. Let's say phi is pi over 2. What does that mean? Well, again, it means it tells you something about where in the cycle the system was when time equaled 0, like when you started your stopwatch. So I plug in, excuse me, I plug in yellow under B, the bottom of the page. I plug in pi over 2 for phi because that's like the value I'm testing. But in red, I plugged in 0 for t. Why did I plug in 0 for t again? Because I always would, because that's the definition of phi. Phi is like an initial phase value. It's where you are in the cycle when the clock starts. So I'm always plugging in 0 for t. I hope you see. So I plugged in 0 for t. I'm in example B at the bottom. I plugged in 0 for t. I plugged in pi over 2 for phi because that's the value I'm testing here to make a point, like I'm doing an example, that example. So I get the cosine of 0 plus pi over 2, i.e. the cosine of pi over 2. Now, I almost should ask you in the chat, but I'm not going to because I've already written on the board and I'm trying to move forward. But hopefully you understand, like if you do a unit circle in your mind or something, the cosine of pi over 2 radians, i.e. the cosine of 90 degrees, i.e. the top of the unit circle, right? The cosine of 90 is 0, right? The cosine of 0 is 1, but the cosine of 90 is 0. It's the opposite of sine. I like to say sine is super, cosine is counterintuitive. Sine goes from 0 to 1, as you might expect. Like as the angle gets bigger, the sine gets bigger. That's like kind of the natural one, right? But cosine does the opposite. Cosine, as the angle goes up, the cosine goes down. That's why we use cosines for dot products, et cetera, et cetera. Okay, so and you can stop me if I'm just trying to. Okay, so the cosine of pi over 2 is 0. Okay, so that means, to finish this example, if phi is pi over 2, then when t equals 0, z, the value of z, whatever z is, the value of z will be 0. What does that mean in English? It means what it should mean. It means the following. Well, in short, it means that when you started your stopwatch, the mass, the whatever, the system was a quarter of a cycle, or it was already a quarter of the way into its cycle. Specifically, it means when you started your stopwatch, the mass was, or the whatever, the system was already at the equilibrium position. Like imagine homework one or lab one or whatever. Like your mass is going back and forth and back and forth, or back and forth and back and forth, whatever. A full cycle would be like from amplitude to equilibrium to negative amplitude, back to equilibrium, back to amplitude, right? That would be a full cycle, fully there and fully back. That's a full cycle. So a half cycle is just there, right? From like positive amplitude to negative amplitude. That would be a half cycle. A quarter of a cycle would be from positive amplitude to equilibrium, right? Now, why am I saying half cycle, quarter cycle? A cycle is 2 pi radians. So a half, always. So a half cycle is pi radians. So a quarter cycle is pi over 2 radians. Or put another way, if your phi is pi over 2 radians, that means the system had a head start of a quarter of a cycle or delay. I mean, depending if you're plussing or minusing. So a head start of a quarter of a cycle. It means when you started your stopwatch, your system wasn't at the amplitude. It was already at equilibrium. If phi is pi over 2, then when t equals 0, z was already at 0. Now, this is just two examples. So I'm saying up until now, we got away with not even knowing about this phase constant thing because we were just tacitly assuming it was 0 without realizing we were doing that because we could, as long as we always started our stopwatch at an amplitude position, which is a very convenient and wise thing to do. But I'm saying now we could start our stopwatch any other place in the cycle we want. It's harder because it's like harder to see what's going on, but we could. And if we did that, we would want to designate that or like track that with a phi constant. Okay, so that's the meaning of phi. I'm obviously want to move on and like relate this to what you're going to start in the lab today with Professor Cologne. I believe it's today. I believe you told me that. I'm trying to get, if I can, to what's going on in the lab today. But let me pause for a second. I'm not assuming this is 5 clear. Can you give me an electronic hand if you think what I just said? I know you need to see examples in a way. In a way, I'm about to show you an example and relates to the lab. But can you just give me an electronic hand if you feel like this is like 3 or higher on a scale from 1 to 5? Is it like 3 or higher? Or can you give me an electronic hand if you hear me right now? Okay. Oh, good. Oh, thank you. And thank you for Alice. Thank you. Okay. And that's good. Okay. All right. I'm going to take that as, okay. Thank you, DJ. And I saw many of you. Thank you. Oh, solid 3. All right. I'll take 3. 3 is good. And by the way, Lena, and I'm not kidding myself. Even for me, I wouldn't rate this much higher than a 3 because, well, I did give you just 2 quick concrete examples, right? I would rate it higher than a 2 because there is a concrete example on the board, but I didn't ask you to work through an example. So how could it be if I get that? Okay, but I'm going to go on because my goal here today, honestly, is to get you positioned for the lab to at least know what's going on in the lab. And the lab is 2 weeks, so you're not going to finish it today. You're going to like collect data and then you're going to what do you call it? Like analyze it next week. So we still have time to talk, but I want you to at least walk in like having some awareness. And also I'm sort of trying to prepare you for the homework, which is due Monday. I'm going to tell you right now, I'm going to move on. Of the 2 goals, my bigger goal is that you don't feel totally disoriented when you walk into the lab. The homework may be a little hard. I'm going to try to set you up for it, but I will totally recognize even more than usual if this homework is a new topic, sort of. So if you get to it and you're disoriented by the homework or whatever, don't steal equations from the web. It will be very tempting to do that. Don't do that. Do your best. And maybe I'll even give an extension or something. Like just at best, try it, or write me write me something, even whatever. I'll get to that in a minute, but I'll understand if, depending on where I get to today, if the homework seems a little hard, and I'll take that into account. Okay, but so, okay. So I'm going to say something. So this is going to get us to the lab. If you're following what I'm saying right now, I'm saying the phase constant is like where the system was in the cycle when you started your stopwatch, like where in the cycle was the system. Now, a very reasonable question would be, okay, but like why? Why would we ever start our stopwatch anywhere but at an amplitude position? Like if that's so convenient and wise, which it is, why the heck would we start our stopwatch when the thing is already like in the middle of its cycle? I mean, can't we just do what we want? Good question. We wouldn't. You're right. We would always do the wise, inconvenient thing if we could, as long as we only had one oscillator. But what I want to get to now, what we need to get to now in the course is, hang on. What if we have a bunch of oscillators? And what if they're similar in many, many respects, but what if they're all going at the same time and they're at different places in their cycle? Then even if you start your stopwatch when one of them is at a perfect place in its cycle, there's no way you can start your stopwatch when all of them are. And that's what we want to look at now for a reason, not just to be hard. We want to look at, so I want you to consider the following situation. Consider that you have a bunch of identical harmonic oscillators, each of which is free to oscillate along, say, a y-axis, but you arrange all of these oscillators along an x-axis. And you and you distribute them uniformly, like equidistantly along an x-axis. So I'm going to make the simplest possible version in my mind. I'm asking you to consider in your mind the simplest possible version of a somewhat complicated arrangement. You've got a bunch of identical oscillators. What do I mean by identical? I mean same M, same K. Like assume they're masses on springs for the moment, or anything that acts like masses on springs. So assume they all have the same M, they all have the same K. That means they're all going to oscillate at the same omega. They're all going to go back and forth at the same rate. Hold on, just to remind you, right? The same angular frequency. But and so now assume that they're free to oscillate in the what we're going to call the y-axis, but then you distribute them equally along the x-axis. So what the English here says, the handwriting says, a vast collection of identical y SHOs, simple harmonic oscillators, distributed uniformly. That means like at equal distances, at equal distant intervals, uniformly along an x-axis. And now assume that they are staggered in phase by a constant step. Okay, and you could say right, like a step, like assume. So assume like this so this oscillator right here that I'm pointing to, that's called the zeroth oscillator. Why? Because it's at x equals 0. Then this would be called the first oscillator because it's at x equals 1, like 1 centimeter. This is at x equals 2 centimeters, whatever. I'm on purpose. I'm distributing them uniformly. So this would be called the second oscillator, etc. Well, assume that each on purpose make it so that each next oscillator is the same is off in phase from the one before it by the same amount that the one before it is from the one before. Like, in other words, again, as simple as you can imagine for something this intricate. Let's even assume in this example that the step is pi over 2, like the example I just did before, radians for each meter. Each next meter, you have another pi over 2 phase thing. So, and this is why I'm just looking at the time. Okay, this is like why we would need a phase like the very zeroth one. And you look at the picture, I'm sort of trying to capture this. The very first one, the very zeroth one, is like at the amplitude position when my stopwatch starts. But at that very moment, say the first one is at the equilibrium position, and say the second one is at the negative amplitude position. So they're right, etc. So each one is another pi over 2 radians compared to the last. And pi over 2 is just an example here, but I think it makes it sort of vivid. Well, if you have that situation, then each oscillator, according to everything we've been saying in this class so far, each oscillator can be described by its own equation, right? The zeroth oscillator is it starts, it's like a everyday oscillator. I mean, when our stopwatch started, it was at the amplitude position. So it doesn't have a phase constant. Its phase constant is zero. So it could be described y sub naught equals a cosine omega t plus zero. Then the first oscillator, well, it's identical in all respect. It's got the same k, the same m, therefore it's got the same omega and all that. And say you start, so same looking equation. The only difference is that that first one has a phase constant. I just can't avoid it because they're not both in the same place, right? That first one is already at equilibrium when the zeroth one is at amplitude. And the next one, so in other words, the first one's a quarter of the cycle way in. The next one is a half cycle in. In other words, 2 pi over 2. And the next one, you see there's a pattern here, right? And it's not a coincidence. If the constant step is pi over 2, then each next oscillator is another pi over 2 away from the original zeroth one. Like all of the fees are being measured. Every single fee is being measured relative to the zeroth one, so to speak. If that, I'll just leave it at that, right? So you see the pattern. Like if I were to ask you, wait, where in the phase is the fifth one? You would say, well, it's 5 pi over 2's away from the zeroth one. It, so I'm all these into one equation. I'm not trying to use the words differently. Sorry, into one big equation. We could put all these together into one because of the pattern. And why is there a pattern? Because we specified. I'm specifying that these oscillators are arranged uniformly along the x-axis, and I'm specifying that the phase step is a constant, right? So I'm saying wherever you are in this arrangement fully determines and clearly simply determines what your phase is. In fact, well, yeah. So I could say something like this. Right, I can collect all these things into one equation, a cosine omega at y equals, and oh, by the way, backing up for a second, notice now my variable is y. At the beginning of this course, the variable was x. The dependent variable was x. Then in lab one, the dependent variable was theta. Right now, I'm saying, oh, no, so sorry. In lab two, the dependent variable was theta. Really, in lab one, in a way, the dependent variable was y. Like your springs were vertical in lab one. So I'm going back to that now. Again, I'm trying to get you one thing that I think people are getting used to is like it doesn't matter what letter I use for the dependent variable. The point is that it's the dependent variable. T is an independent variable, but here in this case, my dependent variable is y, like how high along the y-axis is a given spring. Well, apparently, if you want to know how high a given spring is, I would say to you, I need to know two things. I need to know what time you're looking at this arrangement, but I also need to know where you're looking in this arrangement. Once you specify to me, I'm looking at a particular moment in time and I'm looking over here at the seventh spring, I would be like, oh, okay, plug in 7 for X because the seventh spring is at the 7 centimeter mark. Plug in 7 for X, multiply that by pi over 2. That will be how out of phase that seventh one is. It's going to be 7 quarter cycles displaced from the very zeroth one, right? So plug that in and then plug in whatever time we're talking about, and I'll be able to predict how high that mass is at that moment, right? So this expression would be an expression that would capture the whole thing. For this example, when the step in phase was a constant number of specifically pi over 2. But that's just an example. And it's a vivid example. I think it makes a picture sort of clear, at least in my mind. But there's no rule that we would have to stagger them by pi over 2. So I'm going to generalize this now. You can tell me to go back if you want. I'm going to say from now on, that pi over 2 that I just used as an example could be any number. I'm going to call it from now on K. That is super annoying because we already have a different K in this class. This is a different K. I'm not I wish it weren't, but this is just the standard way. It's also the letter K. It's not the K of Hooke's law. This K is measured in different units. To make that as clear as I can, I'm putting serifs on the K, like I'm drawing it differently, but it is called K. It has a different name. I'm going to give you the name in a second, but this is also a K. Can you just raise your electronic hand if you're clear that this is, well, I'll write it. Hold on a second. Not the K of Hooke's law. This is not I mean, obviously it's all related because we're talking about oscillation, but it's not that same K. Can you just raise your electronic hand if you're with me that this is a new K? Thank you, Sarah. Totally appreciate it. Thank you, Loani. And there was someone else I didn't see whose name it was, but thank you. Okay. Thank you, Lena. All right. Awesome. Thank you, Mom Preet. Okay. I love that whole explosion thing, but sometimes it doesn't show a name. Okay, but great, thank you. And again, right there, those of you concerned about grades or whatever, you could submit for points for just doing that. And also, really sidebar, also because someone, at least one person, seemed to be not totally clear on the following. Every time, and I didn't do it this morning, but every time I send you that thing in Google Classroom that says like class credit so far, that's not an arbitrary thing. And that number will never go down, by the way. It's only going to go up. It's the total amount of points you've gotten on everything so far divided by 50. what that number represents, I know some of you are clear on this and can't stand hearing it anymore, but I think some of you are not clear on this. That number is the number you're going to add to whenever you get your exam score. When you take your exam and you get your score, you add that many points to your exam score, and that's a projection of your grade so far. And then once you take a final exam, you would average them together. But and once you have a lab final, you'll average all those three together. But that number that we're tracking, just so I'm going to go back to this, but I just really want to be clear. It's not a like it's not meant to be a mystery. That number that just keeps going up every time you get something back. That number is what you add to your average, your exam average in the class to know what your grade is going to be. If you care, I'm not telling you to care more about your grades, but I think people do. And okay, wait, is that clear? Is that clear that that's what that number is? Or is it clear now? Yeah. Okay. Thank you, Luani. Okay. Great. 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 Okay. Okay. So, and I'm just saying it because it came out. Oh, thank you, Sharon. I just saw I'm on pre. All right. And Emily, thank you. I'm just saying it because it came up because whatever. And if you ever have any confusion, like I want the grades to be super clear. So if you have any more, any of you, if at some point you're still like, wait, I still don't get how the grading system works, please text me or email me. Like I will explain it. It's slightly unusual, but it's not actually that complicated anymore because I think it used to be too complicated. So I can be okay. Anyway. All right. So back to this. So K, this is a new K. Um, 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 this K, this K, oops, sorry, is always going to be measured in radians per meter. What I mean is not radians, but radians per meter. You'll see because it's the step. It's like how many additional radians you add on to for each next spring in this arrangement or each next position along the x-axis. It's the step, right? So it's what pi over 2 was an example of a minute ago. So once we just say we go general and say pi over 2 could be anything, just call it k, then we can say from now on to capture so in general to capture a collection of oscillators phase staggered in this way. What do I mean by this way? I mean, if they're staggered in phase by a constant amount, such that each one's phase, sorry, if they're uniformly distributed in space and they're staggered in phase by a constant amount, such that the position of one of these oscillators in space immediately lets you know what phase it's in. If it's arranged this way, the way that I'm talking about here, then we can say always for now on. Right. I'm saying that now, in general, in general, if you spread out all these oscillators in this way and you want to predict how high one of the oscillators is, you would need two inputs into that prediction. You'd need to know what time you're looking, and you need to know like which oscillator, where along the x-axis you're looking. Y would be a function now of x and t, right? That function. So we've just gone from, we used to say y equals a cosine omega t. Then we established at the end of last class, in the beginning of this class, we established, oh, you know what? Omega t could have like a phase constant term stuck in there. And now we're saying, you know what? If you, that term would be most relevant if you had a bunch of oscillators, if you had more than one oscillator. And actually, you could set up that term so that it's a function. It could vary from oscillator to oscillator. In other words, I'm saying, in a way, I'm saying that this new idea of phase could be a function of x, a straight line function, for example, such that when x is 0, the phase is 0. But as x gets greater and greater, phi gets greater and greater as a straight line. And what would so a constant slope, right? I'm saying we could set up a situation like this one where where phi increases as a direct proportionality of x. That slope of that straight line, that slope, that constant slope, the rise in phi per the run of x, that could be known as a constant known as k. It could be measured in radians per meter, right? And I'm going to tell you the English word for that in 1 minute. I'm looking at the time. Hold on 1 second. The question is like omega is in English is known as angular frequency. It's the rate at which this thing oscillates per time. K apparently, in a way, is the rate at which, or is the arrangement of its oscillation in space, right? Omega, in fact, let me, well, I'll leave it at that. Like omega is cycles per time, and in a way, K is cycles per space. I'm not asking you, I'm saying rhetorically, what is the English word for this K? If the English term for omega is angular frequency, what's the English term for this K? Well, it's angular something because it's also measured in radians. It's not measured in radians per second anymore. It's measured in radians per meter. But like, what is that? Well, I'm going to tell you by asking you a question. If you really are with me so far, this is like a new thing in a way. Again, remember, I'm trying to set you up for lab 3 here. I'm saying we've been studying an oscillator, but now we're spreading out a bunch of oscillators. And we're spreading them all out so that they're all going to do the same thing, but sort of at different times. They're all going to follow the same rhythm, but they're all going to be at different places in that rhythm at different times. If you stood back, if you let this arrangement go, imagine it's really long. It's like mass, like for a while. And you started your stopwatch and you let them all go up and down and up and down, and you stood back and watched this thing, what would you see? What would this look like? Or what phenomenon would this create? I'm actually asking. I'm not necessarily I mean, it's not a trick question, but maybe it's not an easy question. But just stand back and imagine. I mean, I can imagine that I animate this picture so that each one of these springs is going up and down while the next one is going up and down, but they're all staggered like this. What would this whole thing look like? And I actually am asking. You can direct chat or you can public chat. Or even if you could just acknowledge that you hear me right now, even if you don't know what I'm asking. I mean, do you hear that I'm asking a question? So I'm going to ask it again. So I'm asking a question. Imagine, look at this picture right here. Imagine that that is a snapshot of a larger movie. Like imagine that I animate that so that each one of those springs is going up and down, all at the same time, but all starting at these different positions like that. I guess to be more specific, track like at one moment right now, these things are making a shape. These things are arranged in a shape. Now that shape is going to move if they're all moving. What are you going to see? Even if you don't know, could someone just acknowledge that they hear? Oh my God. I'm just going to go with that. I just got one answer in the direct chat, but it's so correct. I'm just going to go with it. And this person should give him or herself points. One person in the chat just said, a wave? Yes. This is totally, and here we go now. Okay, this is the point of lab 3. This is the point of the everything we've been doing up until now has been setting up the ingredients and the math for this. Okay, I think that if you put a bunch of oscillators together and let them all go, what you would see is a wave. And that's very good, person. You know who you are. Thank you. And if you were thinking that, good, I believe you. And you just didn't like have the guts to say whatever. This is a wave, and it's not actually just like a wave. And the person did say a wave. They didn't even say like a wave or sort of a wave. They said a wave, and they are correct. What I mean by that is if you fix your eye on like mass number 2, right? Like there's like a bump, like a trough, right? There's a valley right there. And there's a valley in that cosine shape right there. But in a moment, if you let these guys go, in a moment, that valley is going to move to the right, right? In a moment where mass 2 is going to be like a peak, a crest. And over here is going to be a valley. And then another moment later, the valley is going to be over here. If you watch with your eye, you're going to see valleys moving horizontally. You're going to see crests moving horizontally in the manner of a wave. And what really makes it a wave, like what makes this a new kind of, now again, it's not just that it's a cosine picture. A lot of people, this gets very confusing to people. A lot of people have been thinking that we've been talking about waves for a month because we keep drawing these cosine graphs. Cosine graphs are not waves. They are wiggles. I mean, I'm not joking. Like this picture right here is a picture of a cosine graph. It's not a wave if it's just sitting there as a picture. But it becomes a wave if not only do you have bumps and valleys, but if the bumps and valleys are flowing in a particular direction. Let me be very specific. I'm going to give you an informal, like English definition right now. I'm saying this is a wave. I'm agreeing with that person, and I'm excitedly agreeing with that person. The reason that it's a wave, it's not just like sort of kind of impressionistically a wave. Like it gives you the impression of wave, but like why? What is it about waves that are wavy? What do we mean by a wave? This wave motion from point A to point B is measurable, reproducible, um, predictable motion from A to B, for which no particle moves. I keep doing that. Okay, I'm going to say this. I'm looking at the time. We have 16 minutes. This is where the thingy thing and the unthingy thing like start to happen here. What I'm really saying informally is wave motion. Wave motion is our first example, big, huge example of unthingy motion, immaterial motion. Everything we've been doing right now has been looking at a particle going back and forth, back and forth. Like technically, it's still standard classical mechanics physics. But now, what we're seeing is a motion that is scientific, that is physics, a motion that is measurable, reproducible, and predictable, a motion from one place to another, from, let's say, y equals 0 to y equals 17, or what you're going to see in lab, like from one lab partner to another today. We're seeing a motion that's going from here to there, and we can reproduce it, and we can measure it, and we can make predictions about it. Like we're seeing a crest go from here to there, and we can literally say the crest traveled 5 miles, and the crest like took 10 hours to do it. So the crest is traveling at a half a mile per hour. So we can predict that the crest will be over here in this amount of time. Like it fits all the rules of physics. We can treat that crest as though it were a baseball. But the catch is that crest that we're tracking with our eye that is totally moving in a scientific way is not a thing. It's literally not a particle. It is not a piece of identifiable, separatable, discrete, or countable, or massive material in the world. Specifically, like what I'm really saying is there's motion from here to there, and the only thing that's moving is metal. Pieces of metal are moving, and there's motion from here to there, but no metal is moving from here to there. More specifically, what I'm saying in the example that we're doing here, it's not always these exact details, but they're always come to this idea. In this example, all of the metal is only and always moving along a vertical axis. Yet we stand back and we observe something happening along the x-axis. The only thing that's moving is metal, and there is motion along the x-axis, but there's no metal moving along the x-axis. That is the essence of wave motion. It's a bunch of materials moving in a certain way so that at the end of the day, we get an immaterial motion. It's very cool. I mean, honestly, I think it's very cool. It's very wild. It's abstract. It's one of the reasons we need such abstract mathematics to describe it, because something real is happening, but it's not tangible, right? So specifically, what is happening? Sorry, just add the word immaterial. The key is that it's immaterial of. So what I'm saying is, and I'm going to move on in a minute. The thing that you're going to look at in today's lab. Now, I'm not saying you're going to do it this way. Okay, you're going to do it from a sort of different perspective. I'll try to be clear about that in a minute. But well, I'll say right now, in the lab today, you're not going to arrange a whole bunch of springs the way I've just said. What you're going to do is take a really long slinky. You and your partners, you're going to stand at various places in the hallways and outside the room with this really, really long, tight, like thin slinky thing, this metal thing. And um and you're going to stretch it. You might want to write this down now. I'm going to give you some pro tips right now about like how to handle this as best as possible. Like you're going to get this really long slinky. You don't have to use the whole slinky. You actually want the slinky to be fairly tight. Between like two lab partners are going to hold two ends of it. You want it to be fairly tight. You're going to go out in the halls and take up space and stuff, but you don't only have so much space to take up. So you're allowed to drop a bunch of the slinky and like let it. You can like let a bunch of it dangle and just hold like some section of it tightly. And then your other partner is going to like walk down there and you're going to hold it at first in a horizontal orientation. That's like an equilibrium orientation. And then you're going to practice a little bit and get better and better. Like one of you will hold still, and the other will like shake one end of the spring as though you're scrambling eggs. And at first, you'll see, of course, and I'm sure you've seen this in many aspects of life, you'll see like a bump travel from you to your partner and ideally back. First thing that I'm trying to say right here is you can watch that bump and everybody will know, oh, it's here, oh, it's there, oh, it's there. What do you and all that's moving is metal, but what do you want? There's no literal metal moving from you to your partner. What's happening is a distortion. It yeah, what's happening is that the whole thing was otherwise horizontal, and then you're all noticing a distortion in the shape of the metal. And it's that distortion, like that little crest or that little trough, that you're all noticing flow through the rest of the metal. The flow is called propagation. Whenever a wave travels, the wave itself is traveling through materials, but the wave is not material. So when not material things travel through materials, we call that propagation. It means flow. That little shape that you watch with your eye that you notice is called a pulse. And what we're saying is when you do that, when you flick your hand and you send this bump to your partner, what's really happening, of course, is that a little bit of metal is going up and then down, and then a bit of metal over here is going up and then down, and then a piece of metal, etc. In other words, what's really happening behind the scenes is a version of all of this. Right? I mean, you're cutting straight to the chase and just making a wave ripple in the lab, but we're trying to argue that a wave ripple is a bunch of little oscillators creating this flow. Okay? The metal through which everything moves is called the medium. We're ultimately arguing that this whole situation can be described, so back to the math of this, we're saying this whole thing can be described by an equation like this, where now this is called angular frequency, and it's 2 pi over the period, right? And this thing, from now on, K, is called angular wave number. Sorry, angular wave number, because once there's a K involved, we've moved from simple harmonic oscillation to wave propagation. But that's what we have now. Unthingy motion occurring in the x-axis due to a bunch of oscillators all happening in the y-axis. So from now on, K is angular wave number. Is it 2 pi over t? No, it's something else. We have 6 minutes. What you're going to try to see in the lab, you're going to create these waves. And let me say this quickly too. First, you're just going to practice by like sending ripples back and forth to each other. But then you're going to try to get them into a steady pattern so that the ripples actually become very, very steady and start canceling each other out so that you end up just getting ripples like looking like this. He'll talk to you about that. And the purpose of that, just to make them easier to look at, the purpose of that is you're going to take a movie. Each one of you is going to take a movie of the waves that you create, like with your phone, um, on these strings. I recommend a short movie, like 20 seconds, 15 seconds, not much longer, because then you're going to upload these movies into your laptops. And you're going to open up Logger Pro, that software that you used last semester, many of you. You're going to open up Logger Pro and access the movie with Logger Pro. Now, again, this is a 2-week thing. Even if you don't finish getting all the data today, it's okay. But the point is, you're creating waves with these strings, and you're going to take movies, and then you're going to create two sets of data or collect two sets of data from these waves. One set of data is where you're going to just focus on a particular slice of the wave. You're going to pick some X value, set it constant. You're just going to look at a slice. In other words, like looking at one oscillator from the picture I made 5 pages ago. And you're going to see how Y is varying as a function of T for one value of X. You're going to see how Y is varying as a function of T for one value of X. And I'm giving away the punchline right now. If you're paying attention, you're going to find exactly what I hope you would expect to find. You're going to find that for any value of X, Y varies as a function of T as a cosine graph. In other words, you have an oscillator at every value of X. But similarly, what you're also going to do is collect data and find. You're going to collect data in a different way. He'll explain this to you so that you pick just one frame of your movie. You'll pick one value of time and look at how Y varies as a function of X, right? And you'll see, just like that snapshot of my picture, that at any given moment of time, what you have also is everything arranged in space as a cosine function. The goal of the lab over 2 weeks is to see that what a bunch of wave pulses is cosines in time superposed on cosines in space, or the other way around, if you like. You've got oscillations, you've got cosines, look at the top of it, in time and in space, coming together to make a wave. I'm almost done. You know from experience in this class already that the interval between any two peaks on the time cosine graph is called T, the period, right? And so omega, sorry, I'm almost done. And so is the class. Omega is 2 pi over that period. Well, what we're establishing now is these bumps are also arranged in space. The interval between any two bumps in space is called lambda, where lambda stands for the length between any two bumps in what we now have as a wave. In other words, it's called wavelength. You've heard of this your whole life. And so K is 2 pi over lambda. That you're going to see that. We're just about done, I know. One thing I'm going to say right now, I think so. The goal of the lab is to make a movie of a wave. You're making a wave, and then you're making a movie of it, and you're going to deconstruct the data into two separate functions, and you're going to find that each of those functions is a cosine function. That's where this whole ship is heading. Again, it's 2 weeks long, but that's hopefully to give you some context. I'm going to say right now, the homework that's supposed to be due this Tuesday, right when this class is over, I'm going to postpone it till Thursday. So I'm going to give you, yes, you can. But I'm going to postpone the homework till Thursday so I have a little more time to talk to you about how to do the homework, because it would be a little hard from this right now. So focus right now on the lab and but what we're saying is we are now moving from simple harmonic oscillations to waves. That's a topic, and it's all possible because of this concept of phase. A wave is a bunch of simple harmonic oscillators all staggered in phase by a constant amount. Okay, that's enough for now. we're done. I'm going to postpone the homework right now, so you're okay with that. Uh, but if there's any questions or anything, I'm staying here for a second. But I'm going to turn off the recording and all that. But have a great day in a great lab, and let me know how it goes or whatever. Okay, so hold on one second.
Bye, Professor. Have a good day.
You too. Thank you. You too. Okay, hold on.